Hello everyone and welcome to the PCD for CodeChef Starters 196. Okay, today we're going to discuss problems A to C of Division 2. Okay, so today we're going to discuss the problems sugar limit, append average, and beauty in everything. All right, guys, because to be honest, the next question swap sum was I think segment trees, so didn't quite get it in contest. All right, yeah, okay. How many questions did you guys get? Am I audible? Can someone just put in chat if I'm audible? I guess I'd be audible right now. Yeah. How was the contest, guys? You can put your division and how many questions you solved. Just make it a bit interactive. Come on. How was the contest? Good. Okay. Mini says it was good. All right. Okay. So before we start, uh, if you haven't, seen it yet, do check out TL Eliminators courses where we provide self-paced courses for all levels of cognitive programming, right? So based on your current level, if you're a complete beginner, choose level 1. If you can solve, let's say roughly one problem in Codeforces Div 2 or one problem in like starters, then you should take level 2, similarly level 3 and level 4, right? They're all based on what topics you need to learn to go to the next stage of your CP journey, as well as the course also comes with like curated practice problems, hints and video solutions for each of the problems, as well as doubt support and leaderboard and stuff, right? So do check it out. There's in fact a sale which lasts until the end of this month, right? When everything is at a discounted price. And anyways, even the original price is very affordable in my opinion. So yeah, right. Okay. Today we'll be discussing three problems of Div 2 because yeah, okay, so Mohit, I guess today we'll not be discussing fourth and fifth since I could not also solve fourth and fifth. I could solve three problems of Div 2 today. Fourth one, I have a rough idea that it was segment trees, but I did not know how to quite implement. Fifth, I don't have much idea. All right, Mohit, we're gonna start soon. No need to be that impatient as well, right? I'm just checking how you guys did the contest. Okay, let's get started. We're gonna start as usual by starting from the easiest problem and go on to the harder ones, right? Because everyone is at a different stage, right? And that's why we discuss all the problems at least once. Okay. So I know the title has not changed yet. I think the title still says A to E, but today we'll be discussing A to C. Maybe a little bit of D. We might discuss the idea a little bit, but I did not implement it. Yeah, yeah. No, I realized it was segment trees during the contest, but I was not exactly sure how to implement it. Okay. So the first question is pretty simple. Sugar limit. Chef bought n different snacks, and now he needs to decide which ones to eat. The ith snack has a tastiness of A of I and contains B of I units of sugar. Chef wants to limit his sugar intake, so he will choose some non-negative integer L, and he can only eat a snack if it has at most L units of sugar, okay, which satisfies B of I less than equal to L, okay. So he does not need to eat every snack which satisfies B of I less than equal to L. He can skip some of them too, okay. Let S denote the sum of tastiness values of all snacks which chef decides to eat. Then his satisfaction equals S minus L. So L was the maximum limit of sweetness. So S is the sum of satisfaction values. So then his total satisfaction equals S minus L. What is chef's maximum possible satisfaction if he chooses the value of L and the snacks he eats appropriately? Okay. And then we can see the constraints. T goes to 100, N goes to 100. So very small constraints. A of I, B of I go to 100. Note that A of I can be negative also. So it's between negative 100 to 100. Okay. So AFI is the tastiness value of the snack. Okay. So This is problem A, I guess. Problem A, sugar limit, right? Problem A, sugar limit. Okay. So how do we approach this problem? Well, okay, we can see that since it's an easier question, I'll jump directly into the intuitions, right? There's not much to discuss. Intuition. And the first idea is that, okay, so let's say we pick an L, okay? Let's say we pick the value of L. We pick the value of L. Then to maximize S minus L, which is the satisfaction value, right? Then we should maximize S, all right? And how do we maximize S? So to maximize S, S is the sum of A of I of the picked snacks, right? And we can only pick snacks such as B of I is less than equal to L. So for S equals to sum of A of I for all I such that first condition is A of I should be positive, right? Because if A of I is 0 or negative, or in fact, if A of I is negative, it's just going to reduce S, and we want S to be as much as possible. So we'll pick all the positive values of A of I such that B of I is less than equal to L. Okay. So this is the main intuition behind the problem, that if we have picked a value of L, then to maximize S minus L, we should maximize S, correct? Okay. So now what is the next intuition to have? The next intuition is basically um, sort the pairs, sort the pairs A of I, B of I. Okay, so we're going to store them like a vector of pairs by the value of B of I. Okay, by the value of B of I. Fine. Now what this does is basically it makes your snacks in order of how much sugar they have, right? So let's say a snack has tastiness 3 and its sugar is 5. The next snack has tastiness 10 and its sugar is 6. The next snack has tastiness minus 3 and its sugar is 7. The next snack has tastiness, let's say, minus or maybe plus 2 and its tastiness is 11, let's say. Okay. So once we have it in increasing value of sugar, okay, once we have it in increasing value of sugar, now we can see that the only values of threshold L, the only values of threshold L which are important to us is either if the threshold L is before everything, right? If the threshold L is like equal to 0 or something, in which case we eat no snacks and our answer will be 0, right? Otherwise, the only relevant values of threshold will be keeping the threshold here at 5 or here at 6 or here at 7 or here at 11, okay? Why is that? Because if we keep the threshold higher, we are trying to maximize S minus L, right? So there's no point keeping it any higher than the snacks we intend to consume. So if we intend to consume a set of snacks for the score of S, then the threshold should be kept as the max B of I of that, right? So basically the only values of L to consider, only values of L to consider are the values of B of I, okay? Are the values of B of I. And if we sort by B of I, and if we sort by B of I, now this is the final part of the problem. If we have sorted by B of I, then what happens to the sum S? S is simply the sum of all I dash less than I, right? Or less than equal to I. So if we're at sum B of I and AI which is greater than 0, right? All the positive AI which is less than my current position. So let's say I say that L is equal to this point. L is equal to this point. L equals to 7. Then basically all of these positive A of I, the positive tastiness values will sum. So here negative 3 is not positive, so we're not going to sum it. But 10 and 3 we're going to sum. So we'll have S equals 13, L equals 7. Okay. So basically the values of S and L in this example, uh, so basically the values of S and L in this example are going to be something like this. S equals 0, L equals 0. So that can be just handled by the base case of 0, right? Then here we can have S equals 3, L equals 5. To include this, we would have S equals 13, L equals 6. Here we would to include this, we would have S equals 13 because this is negative, so it won't be added to the sum, right? So we can just make the sum left to right, like a prefix sum. And the L value will be simply the value of B of I. Okay. So here S will be 13, 14, 15, and L will be 11. Okay. So basically, what is our final algorithm? Let's write it down. Final algo, sort pairs A of I, B of I by B of I value. Okay. Let answer equal to 0. Let sum equal to 0. Okay. Then for I from 0 till n, okay, what we're going to do is sum will be added by A of I. Okay, because now we can take A of I if A of I is greater than 0. Otherwise, it will just reduce sum, right? So we might as well not take a snack which is reducing our sum. So sum will be adding of A of I if A of I is greater than 0. And then answer will be updated to, so we want the maximum possible answer. So it will be updated to maximum of answer and sum minus L. And L is simply B of I at this point. So this will be the for loop. And then finally we can print our answer, cout answer. Okay, so this is the pseudocode for the problem. What about the time and memory complexities? There is no additional memory complexity, just O of n. And time complexity will be n log n because we're sorting. So time complexity is n log n. Memory complexity is big O of n, right? So that's how to solve this problem. Uh, Pretty simple problem if you're exposed to greedy ideas, right? But although the logic is nice to explain, I guess. So here's the code. It's pretty much the same. Here, instead of checking if A is greater, here I'm just directly setting the value of A to be max of A and 0. So if it's negative, it will simply become 0, right? And also, instead of storing it as pairs of A of I, B of I, I've stored it as pairs of B of I, A of I. Since we're sorting with respect to B of I and I don't want to write a custom sorting function, that's why I did that. Okay. So instead of storing A of I, B of I, I'm storing B of I, A of I. That's why you see that I'm adding V of I dot second, and here I'm subtracting V of I dot first. But the logic is entirely the same. If you're interested, you can pause the video and you can see the code. Okay. All right. Any doubts in that explanation, or otherwise we'll move on to the next question. Div 2b was simpler than A. I don't know. I would say both were pretty similar. The thing was div 2a is a more common and known idea. That's why it was kept before, I suppose. How did you do it? You did brute force for div 2a. Not sure what brute force you did, but okay, as long as you solve the question, doesn't matter. The constraints were pretty small, right? But O of n solution existed, so that's what came to my mind first. I implemented that. Okay, let's move on to problem B. Problem B, and what's the name of the problem? Let's see, it's append average. Okay, so append average is less common than A. That's why I think it was kept afterwards. If you see easiness, it might be the similar questions in easiness level, maybe. Here, you basically need to observe how time complexity works. You need to be clever about that. Okay. Append average. Okay. So let's quickly read the question. You're given array A of length n. You must perform the following operation exactly k times. Choose two indices I and j. Then, if their sum a of I plus a of j is even, then append a of I plus a of j by 2 to A. If it is odd, append a of I plus a of j plus 1 by 2 to A. Okay. So n is increased by 1 after this. Find the minimum possible sum of the array after performing this operation k times. Okay. So we have to minimize the sum of the array after performing this operation k times. Okay, brute force means he selected every L and then did greedy. Yeah, okay, so he didn't sort. That also works. Yeah, I understand. I will not be discussing the full solution for swap sum. Actually, because I didn't solve it in contest myself. I did have some ideas, so maybe I might discuss rough ideas, but not the solution. Okay, so how do we approach this question? And first thing first, we have to see the constraints. So it's normalish constraints. N goes up to 10 to the power 5. But observe that A of I goes up to 10 power 5 is normal. K also goes up to 10 to the power 5, right? And this might be a problem. If K was simply, sorry, K goes up to 10 power 9. If K was simply 10 to the power 5, it might be easy to implement, right? Just a simple question, but it's 10 to the power 9, so we have to be careful. We cannot do a O of K solution. Okay, we cannot do a O of K solution. Okay, so how do we solve this question? Okay, so one thing should be immediately obvious, which I don't think I should tell that much. We want to reduce the sum of the array, right? Reduce the sum of the array. We want to minimize it, right? We want to reduce the sum of the array as much as possible. As much as possible. So each time when we add two elements, each time we want the new element to be also as small as possible. We want the new element added, the new element, whenever we do this operation, we have to do the operation k times, right? So we want the new element to be as small as possible, right? Okay. So what next? What we need to see is that, right. So how are we defining when we choose some ij, pick ij, and what are we doing that ij? Basically, they have written a different case for even and odd. But if you want to write this, you can simply write it as floor of a of I plus a of j plus 1, right? Divided by 2. So it's something like a average of a of I and a of j. Okay, roughly the average of a of I and a of j rounded up, right? Or they have taken like ceiling of average of a of I, a of j. That's what this expression means. Each time we're doing the operation, we're adding this element to the array, right? And also we want this array element to be very small. Using min heap, yeah, using min heap you can do it, but why even waste that much memory? You can do it with just two variables, correct? Why even we waste that much memory to use a min heap? So the solution I'll tell will only use constant storage, I guess. Anyways, so let's continue on with the solution. Okay, so now I'll give you a simple example. Let's say we have an array like 1, 13, 20, 35. Okay, and we have k equals 2. So now we need to add a new element. Now we basically need to add a new element, correct? And what we want here is um, the new element should be as small as possible, right? And we can choose any two elements and basically add their average, right? So always it's best, intuition, always best, always best to choose smallest two numbers, smallest two numbers and add the average, right? And I think this should be easy to prove because if we pick anything larger than the smallest two numbers, then the new number added will also be larger, so it's going to reduce the sum anyways, right? And add them. So in this array, we will choose 1 and we will choose 13. We'll take the average, which is 7, and we'll add that as the next element, right? So that's 1, 13, so 1, 7. I'll just put it in sorted order for convenience. Becomes like this, right? Now again, we choose the smallest two numbers, which is this one and this one, and we can take the average and add it, right? So average will be 4, right? So it becomes 1, 4, 7, 13, 20, 35, right? If the average is fractional, we should take ceiling of it. That's all the question says. Okay. So now we have made the key observation. Key observation. Always pick smallest two numbers. Okay. Right? So in the whole array, we really don't care about the others. We just need to take the sum and um we just need to take the sum and um after that we just need to keep track of the smallest two elements of the array of the vector or whatever. Now, once you think of this, you can think of very simple solution. Just keep like a heap or something and then find the answer. But the thing is, because k goes to 10 to the power 9, remember? So that many new elements will get added. So we cannot store them all in memory, right? So how do we approach this? So one interesting observation you can make is, let's say we have 1 and 100, okay? So what happens when you take average between 1 and 100? Basically, it becomes, so 1 plus 100 will become 101, and 101 by 2 is how much? It's 50.5, right? Which becomes 52, correct? So our new array becomes basically 152, right? And since we only need to keep track of smallest two numbers, we can just add 52 to the sum. We can add 50 to the sum, and we can keep the smallest two numbers only, right? Now the smallest two numbers are 1 and 52. Now again we do the same thing, 1 plus 52, 53, whole divided by 2, which is, how much is that? It's 54 by 2, which will be 27, correct? So 1, 52, 27, and we can add 27 to the sum, correct? We can add 27 to the sum. Now what? Now we can only keep track of 27 because um, 52 is not required. Now what happens? 1 plus 27 is 28, divided by 2 is 14. So we have 114. We can add 14 to the sum. Next what? Next we can add 1 plus 15 is, sorry, 1 plus 14 is 15. And then if you divide by 2, it's 8, right? So we can add 8 to the sum. Then it'll become 1, 5, and we can add 5 to the sum, right? Then after this, it's going to become 1, 3, and we can add 3 to the sum, right? And that's going to become 1, 2, and we can add 2 to the sum, right? Now what happens after this, right? Once it has reached 1, 2, what happens after this is basically this number never changes, okay? Because they're next to each other. So either both of them become equal, either it becomes like 1, 1, or it becomes something like 1, 2, in which case 2 plus 1 is 3, right? And 3 ka average is 1.5. So 1.5 will again become 2. So again, the next element will be 2, right? The next element will be 2. If we discard and only keep the smallest 2, this will be the array. And basically after this, it's going to keep repeatedly adding the sum of 2. Okay. After this, no matter how much k is remaining, it will just repeatedly add the sum of 2. So basically, can you observe what happened here? Basically, what is happening is um, each time sum gets added with average of smallest two elements. So basically, average of a of 0, a of 1, and iska ceiling, right? It get added with this, basically this value. Then the second smallest element becomes this average. Okay, the second smallest element basically becomes this average, right? And then this continues. Repeat this until at this point, at some point, if the second smallest is equal to the average of smallest and second smallest, okay? So when that happens, it will keep getting repeatedly added, right? It will keep getting repeatedly added. So we can just stop and remaining we can just add. So while we are doing this, let's say k steps have passed. So we're doing k minus minus. For the remaining k steps, we can simply add the answer k times a of 1, okay? Because we know that all the averages will come out to be the second smallest and remaining k. So this is the remaining k. In all those steps, only this new element will be added. So we can add that to the sum, okay? So basically s plus equal to this if there is any k remaining, if k greater than 0, okay? Difficulty of this will be how much? I guess it would be something like on CF, it would be like 1200, 1300 maybe. Maybe 1200 on CF. But again, it's a code chef question, so I'm not sure how to tell it in terms of code chef rating. But in CF, I think this would be at 1200 because it's mainly a time complexity question. We just need to know how to think of time complexity here, I guess. Yeah. So let's write down the logic for one final time. Okay. Pseudocode. So in the start, sum will equal to 0. Okay. Then we input the array, input the array, and for each element of array, sum will be plus equal to that element. Okay. Let's call something. So let smallest, let's call it smallest, okay, equal to the smallest element of the array. And second smallest, let's call it second smallest, too small. That is the second smallest element of the array. Okay. Now what we can do is while k minus minus, okay, while k keeps decreasing, the sum will be added with um, the average of smallest and second smallest, right? So ceiling of average, so smallest plus second smallest plus 1 whole divided by 2, right? And this is happening while k minus minus. And then we can say that if second smallest is equal to this average, then we can say that it's going to repeat this for the remaining k as well, right? So we don't need to do it manually. We can just multiply by k times. So we can break here and we can multiply by k times. So I'm going to write break here. And otherwise, we can set second smallest equal to this average because now this average will always be between the smallest and second smallest, right? So it's going to be smaller than the second smallest for sure, right? And then if k is still greater than 0, if k is still greater than 0, then the sum can be added with k times second smallest because all the averages from now on will be the second smallest. And then we can simply print sum. Okay, print sum. And this is the rough pseudocode for this. Now the big question is, at what time will the average stop decreasing? Okay, so the main idea was at some point in time, the average will stop changing, right? So let's say if we have 7 and 13, right? Their average is going to be how much? It's going to be 7 plus 13, which is 20. 20 by 2 is 10. So the array becomes 7, 10, 13, right? 7, 10, 13. And then after this, what does the array become? Um, 7 plus 10 divided by 2. So that's 17, 18. That's 7, 9, 10, 13, right? Now what is 7 plus 9 whole divided by 2? That is simply 7, 8, 9, 10, 13, right? And then after this, what's going to happen? 7 plus 8 whole divided by 2. So that's 15 plus 1. So that'll be 7, 8, 8, 9, 10, 13, right? And then after this, the array will become 7, 8, 8, 8, 9, 10, 13. And then after this, the array is going to become 7, 8, 8, 8, 8, 9, 10, 13. If k is still there, that's what's going to happen, right? So what we're going to do is we're basically going to stop at this step itself. Or sorry, so stop at this step itself because 8 came 2 times, 8 got repeated. And for the remaining k, we can just do k times 8 and we can add that to the sum. Okay, for remaining k. Remaining k times 8, we can add that to the sum. Because every time the average is coming out as 8 only, right? And how many steps does it take to converge? How many steps are here? Number of steps. So for two numbers average to converge, right? What we're basically doing is a of I and a of j, and we're taking their average. And each time we're replacing a of j with the average again, right? We're replacing a of j with the average again. So it's easy to show with some math that the number of steps taken, number of steps till they converge, is is log of a of j minus a of I. Okay, or it's log of second smallest and smallest. A of 1 minus a of 0. Okay? Is the log of the second smallest minus the smallest. That many steps it will take to converge. And why is it logarithm? Because each time we're dividing by 2, right? So if you set, um, you can just set a of 0 as 1 and a of 1 as the maximum possible value. So each time this value is getting halved, right? Each time the value is getting halved. So that's why it's log base 2 of this. Okay? It's log base 2 of this. Okay? Log base 2 of a of I minus a. So these many steps it takes to converge over here. And that's about it. So this is the full solution. What is the time complexity? Let's discuss that. Time complexity of this solution. Time complexity. And the time complexity is simply big O of n. Why is it big O of n? Just to read the input. And then after that, the number of steps are simply log of uh, uh, so not exactly log, it will be something like min of k and log of a of 1 minus a of 0. So this is the rough time complexity for the problem, right? If you want to do it in the most optimized way, um, and be technical about it. And what about the memory complexity? The memory complexity. So we can roughly approximate this as big O of n plus log of a. Okay. So this is the rough approximation of the time complexity. And the memory complexity simply needs to be big O of 1 because we don't need to store anything extra. We don't need to store the elements. We just need to store the sum and we just store the smallest element, second smallest element. So basically 3 variables, mostly like 3 important variables we have. So that's constant complexity, big O of 1. Okay. Let's take a quick look at the code for this problem. Okay, so here is the code. We take in n, we take in k, okay, and we're inputting that. So here I made a vector, but this vector, don't be fooled, it does not contain n elements. This vector contains at most 2 elements, okay? This vector will always store max 2 elements, okay? So it's constant time complexity only, okay? Constant time complexity only, fine? So keep that in mind. Sorry, constant memory complexity, not time complexity. Okay, this vector will always store 2 elements. This is just for convenience. And this is the sum variable. Fine. I input each value for the array. So I input each value. I add it to the sum. I add it to this vector. I'm going to sort this vector. So at most 2 elements. So the sorting will be, sorry, at this point it will be at most 3 elements. So the sorting will be also constant time. Okay, big O of 1 sorting here. Right. So go through the code carefully after the video. If you're not understanding this, just pause it and go through it. So that's why I'm making sure that if my vector size is greater than 2, I'll pop it back, right? So basically, I just want the smallest 2 elements, and this is just a hack to get the smallest 2 elements of my array. That's it. I just want the smallest 2 elements. Now, while k minus minus, I'm going to take the smallest element and second smallest element, take their average, add that to the sum, and if that's equal to the second smallest element, I can break. Otherwise, I set that to the second smallest element. Okay, and I repeat this until k gets over or until this runs out, until that log of a of 0 minus a of 1 condition hits. If k is still greater than 0, I can add k times v of 1 to that sum and I can print the sum. Okay, so that's all for the code for this question. Any doubts, you may put it. Yeah. Feels like 1000 instead of 1200. Depends on you. If you have seen these kind of questions before, it's much easier. I don't know. Yeah, I know you don't need this much optimization, but um, like this was the first thing which came to my mind. I also usually don't overly optimize, but it came to my mind, so I did it. The way I set up my IDE is Sublime Text and it's some themes and the build system and stuff. The build system, you get guides on the internet how to set up the build system. If you know some basic shell scripting, then you can set it up better. Anyways. Okay, so this one, I think my implementation is not the best for the third problem. Um, let's see. The problem itself is simple, the solution itself is simple, but my implementation might not be the best. I'm sure some people in the chat might have better implementations. Let's see. The output input windows parallelly. On Sublime, you have layout. So if you go to layout, you can add columns and groups to the right. And then I have like a custom script which I run. So anytime I want to build or the whole layout from scratch with new files, I just run this custom script and it opens up. So a bit of rising, I guess. So personal queries like that, I can't answer right now during the session, maybe during the end if you want. Or you can go Google it, right? Nowadays, everything is available on Google, so it's fine. Okay, let's do C now. Let's not waste time. Beauty in everything. Uh, a binary string B of length n is called good if there exists an integer k satisfying the following properties. 1 is less than k is less than n, and also k divides n. Okay, so simple definition of k should be some element less than n and greater than 1 which divides n. Okay, so proper divisor. That's called a proper divisor. Consider a binary grid G of dimensions n by k times k. So basically each divisor has a pair, right? Each divisor of some number has a pair. So basically we're considering that pair such that its row major order equals B. Okay, such that its row major order equals B. Okay. Um, for each 1 less than equal to I less than equal to n k. So what does row major order that basically defining? It means that when you read it row wise, like if this is the string and if k is equal to 2, reading it row wise means 0, 1 goes here. And after that 0, 0 goes to the next step, right? 0, 0. Then finally the 1, 1 comes last. So basically that's what we mean by row major order, or basically row wise we're reading the grid. Okay, we're filling the grid like that. Now once we fill the grid, they have a condition for us. Every column of this grid must at least contain one occurrence of 0 and one occurrence of 1. Okay, so every column, for example, you can see here, there's one occurrence of 1 over here, there's one occurrence of 0. Here also there's one occurrence of 1 at least and one occurrence of 0. So every column must have an occurrence of 1 or it must have an occurrence of 0. Okay, does that make sense? Okay. Now, they also give an example where there's not an occurrence of 1 and 0. So in this column, there's both zeros. So that's why this is not it's not good. Okay, this string is not good. So that's how they define a good string. A binary string B is called beautiful if it contains a non-empty subsequence that is good. Okay, a binary string is called beautiful if it contains a non-empty subsequence that is good. That is basically if for some string there's any subsequence which is good, then that string is beautiful. Okay. Now you are given a binary string A. Find the length of the longest substring of A which is not beautiful. Okay, so the question is a bit convoluted. I can agree with that, right? Like first you're given one definition, and then you're given like definition of how to make row-wise grid. Then you're given the definition of good. Then you're given the definition of not good. Then the definition of beautiful, and then the definition of not beautiful, right? And that's what we're trying to find. And here subsequence is there. Here substring is there. The question is a bit complicated, but it's very basic. Once you understand what like they've just made a simple problem into a lot of masala and they've made it complicated. Once you understand the question, it's pretty simple. Okay. The statement is pretty wacky, but yeah. So what is the input? The input is n. N goes up to 2 times 10 power 5. It's a binary string, so that means each character is a 0 or a 1. Sum of n does not increase 2 times 10 power 5. Okay. So this is beauty in everything. Everything. Okay. So we'll have to decompose the problem a little bit. Okay. So let's take an example and try to decompose the problem a little bit. And I'll rewrite the problem also later, so it becomes simple. So we have 1 0 0 1 0 1 0. Okay. So here basically what we need to do is we need to find a substring max length of not beautiful substring of not beautiful substring. Okay, that's what we need to find. So for example, if let's just pick one random substring. Okay, now how do we know whether this substring is beautiful or not? And a substring is beautiful if we can have some subsequence here such that we can form that grid using divisors of the subsequence such that each column has 0 or 1. Okay, so I'll show you one way to do it here. I'm going to choose uh, 1 0 and 0 and let's say this 1. Okay, so I choose these 4 elements and I'm going to form a 2 into 2 grid. Okay, so I chose 4 elements. 2 into 2, 2 divides 4, right? And so that's why I'm going to form a 2 into 2 grid of these 1 0 0 1. Okay, and as you can see, this is a row wise grid or row major order grid. Okay, row major order for that subsequence which shows. Okay, now here you can see in column number 1 there is a 1 and there's a 0. Similarly, in column number 2 there's a 0 and there's a 1. So this is a uh, good subsequence. Therefore, this is a beautiful string. Therefore, this is a beautiful string, beautiful substring. And basically, we can say that this is not a not beautiful substring, right? It's a beautiful substring. So this is not a good candidate for a max value, right? We want to find the max value of not beautiful substring. And here what we found a beautiful substring. Okay. So now how do we go about this? Okay. So let me tell you one of the major intuitions, which I'm not exactly sure how you would come across this. Like I just got it instantly, but maybe after playing around with some strings, you will see that only strings or subsequence of length 4 matter. Okay, of length 4 matter. Only subsequence of length 4 will matter. In other words, only 2 into 2 grids matter. Okay, why do only 2 into 2 grids matter? Because first of all, um, the definition of this grid, which makes a subsequence good, is that there should be some 1 less than k less than n, right? So there should be some proper divisor. There should be some proper divisor. And n equals 1, n equals 2, n equals 3. They don't have any proper divisors, right? N equals 1, 2, 3. They don't have any proper divisors. So the first value which has proper divisors is 4. Okay, the first value which has any proper divisors is 4. And that is a 2 into 2 grid, right? The divisor of 4 is 2. So we have a 2 into 2 grid. And what I mean by this is, um, if we have any larger grid, if we find a larger grid of let's say size n into m, then a subsequence of that, let's call it larger good grid. Okay, subsequence of that will be a 2 into 2 grid, which is good. Okay, so what does this mean? That means that we only need to care about 2 into 2 size grids, which are good. And let me show you an example. Let's take the grid which they gave. So they gave an example of a good grid, right? The good grid is, let's say, 0, 0, 0, 1, 1, 0, 1. Okay. Now what we can do, since we are picking subsequences, is that we can only pick these two, and these two. And we can say that, okay, if we had just picked these two, sorry, not these two, wait. We can pick this, and this, right? So we can say that if we had just picked this, wait, again, it's kind of wrong. We can pick, let's see, give me a second. Okay, we can pick these four, right? We can pick these four because they have both a 0 and a 1 on both sides. So what happens here is, if we take this subgrid, right, it's also a subsequence of that original subsequence. Here, this is also good. This is also good because there's 1, 0 and 1, 1 in each column, right? So basically, even if we have a grid which is very large, let's say it is like 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, something like this, and then 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, something like that. Even if we have a very large grid, which is good, we don't need to consider larger grids. We only need to consider grids of size 2 into 2 because each of them will have like a subgrid, which is a good grid of a smaller size, right? So for example, we can take a subgrid over here as 0, 1, 1, 0. So this is one subgrid, which is like only of size 2 into 2, and that's also good, right? So there's no reason to check the whole sequence, no reason to check this whole grid, check this whole subsequence, when we only need to check good subsequence of size 2 into 2 or size 4 subsequence. And that's the explanation or justification behind what I said here. Only strings or subsequence of length 4 matter. Okay. So this is, I guess, the main intuition for the problem. Main intuition that only subsequence of length 4 matter. Okay. Because if there's a larger grid or a larger subsequence, then you can always simplify it by converting it to a length 4 subsequence. Okay. Yeah, that's exactly what I'm saying, entertainment.exe. If you're given a string, you can remove some like if you're given a subsequence and you can remove some other elements and make another subsequence of length 4. If you can make a good one, then the whole thing is also, then you can say that, yeah, the whole thing may or may not be good, right? Basically, every good subsequence has a smaller subsequence of size 4, which is good. And basically, I was just trying to prove that, but you can write the intuition in just one line. You can just write this, right? Okay. So what is the next step? What are the good subsequences of size 4? Because we only need to consider subsequences of size 4. Okay. So for size 4, we'll have 2 into 2 grids. So 0, 0, 0, 0 is obviously not allowed, right? Because we need two zeros and two ones over here. So what are the possible ways? One way is this. The other way is this. The other way is this. And the final way is like this. Okay. And you can check that these are the four ways and they correspond to a subsequence of 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Okay. So these are the subsequences corresponding to these grids. And all of these subsequences are good subsequences. Okay. These are the, you can say atoms or something, unit subsequences, which are good. Okay. These are the length 4 good subsequence. Any good subsequence, from what we said earlier, any good subsequence of length greater than 4, will contain these as a subsequence, as a subsequence. Okay. So that's mainly the main idea over here. So let us now simplify the problem. simplify the problem using this above knowledge. And what does the problem become? The problem becomes basically find the longest substring, which is not beautiful, right? So we need to find the longest substring, find the longest substring, which does not have, does not have 0011, 0110, 1001, or 1100 as a subsequence. Okay. So this is what the problem is actually asking us. Once you realize the fact that only length for subsequences should be considered. Okay. So this is the simplified version of the problem. Okay. And that's all the problem is asking us. Now, if you could not have simplified till now, you can just pause the video here and go try and implement this part yourself, right? Yeah, I did think about swap sum. Yeah, it was segment tree with, I'm not sure if you need set or not, but yeah, you just need a segment tree and a clever merging operation for swap sum. But I could not implement that during contest. Anyways, so this is the approach for, this is the simplification for the problem, beautiful substrings, right? So how do we implement this? There are multiple ways you can use. I'm not sure. There'll be probably some standard way, but some ways I thought were like sliding window that could be used, right? And another approach is to maybe keep like decks or something, but I'm not fully sure how it would work. But let me tell you my approach. So it's not the cleanest, but it works, I guess. My approach. So at each position, I store the index of previous occurrence of 0 and also store for 1. Okay, store for 1. Also store for previous occurrence of 1. Okay, so what does that mean? I'll have two arrays. One is going to be previous 0 of I, which will have the previous occurrence of 0 less than equal to I. So at some index less than equal to I. Similarly, previous 1 at position I will have the previous occurrence of 1 at some position less than equal to I. Okay. So now what I need to do is I simply need to find if this pattern, basically the largest substring which does not have this as a pattern, right? So what I need to do next is for every I, I'm going to try and find where such a pattern will begin. So what I'm going to say is for every I, so first pattern which I want to check is, let's say 0011. So I'll check this pattern like this. For a given I want to find the first previous one position, right? Previous one position, go back one step because I've already taken this one to be this part of my subsequence. Then again, I will find the previous one position, go back one step. Then I'll find the previous 0 position, go back one step, and previous 0 position, and go back one step. Okay. And basically, if I can do all this, if I can find a 1, a 0, and 0, then I find which position this 0 was. Okay. Which position this 0 was. And basically, what this means is, let's say I had a bunch of values. I have a 1 over here, a bunch of values, 1, and then let's say 0, 0, right? And then, so I'm searching for this pattern. So if this is my I, the previous one will take me here. Then the previous one is going to take me here. The previous 0 will take me here. And the previous 0 will take me here. So as soon as this becomes my substring, it's going to become invalid, right? So I can say that my validity will last until this last position. So if I can form this, right? If I can form this and this -1 thing does not take me out of bounds, right? I should get all the 4 characters. Then everything after the last character can be taken as valid or at least free from this, okay? Free from this substring. from this subsequence, right? So that's the way I approached it. So I'm using two arrays, previous one and previous zero, which for every I hold the index of previous occurrence of 0 and 1. So then if I repeatedly find the previous occurrence, here I need to make sure that my index does not go out of bound. So I use some if else over here. It's not that simple, but using some if else or using some count variable, we just need to make sure that we did all the 4 steps, right? We got first 1, then we found a 1 before that, then we found a 0 before that, and we found a 0 before that, right? So we need to make sure all these steps occurred. And then finally, once we have found the last 0, this whole thing after the 0 till I is like a valid substring which is free of 0, 0, 1, 1. Okay. So basically, do this for all four. That is 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1. So we do this for all 4. And then basically we find some valid limits, right? So let's say we try for 0, 0, 1, 1. So if we try for 0, 0, 1, 1, our limit becomes this much. Now we want to try 0, 1, 1, 0, 0, 1, 1, 0. So that's our limit, but already we have a smaller limit, right? Now we want 1, 0, 0, 1. So this is the previous one, 0, 0, 1. So then this is our other limit, right? So basically we can say that this much, these 1, 2, 3, 4, 5, 6. 6 are a non-beautiful substring. Okay, these 6 are a non-beautiful substring because they don't have any of these 4 as a subsequence. Okay, because they don't have any of these 4 as a subsequence. Any 4 as a subsequence. And since the size we are checking is only 4, the amount of jumps we are doing is also 4 over here. As you can see, the amount of this jumping we are doing is only 4. So basically in time complexity, 4 times n, right? Big O of 4 times n, which is the same as big O of n itself, right? We can check. Um, we can check for each I, what's the maximum substring, max length substring, ending at I, which is not beautiful, okay? Which is not beautiful. And to be not beautiful, it just needs to not include any of these 4 as a subsequence, right? That we already discussed. Okay. So if we do this approach, let me just summarize it. We have to make 2 arrays, which is previous 0 and previous 1. We can make both of these in order of n. Then we need to do this traversal through each ending value I. We need to try all the 4 good subsequences and make sure that they're not there. Or we need to restrict it to find the valid area where they're not there, right? And then once we have found that, we can find the length for this given I value. And in the end, we can take the maximum of all I values, of all the lengths we got from all the Y values. So the time complexity will be big O of n. And because we need to store the binary strings also, the memory complexity will also be big O of n. Okay. The memory complexity is also big O of n for this approach. If there's any easier to implement approach, do tell, because while implementing, this looks a bit ugly because for each string, we are doing this previous logic, right? We're doing the previous logic. So let me go through the implementation clearly once. We take in n and we take in the binary string s. If n is less than equal to 3, then obviously if n is less than equal to 3, it cannot contain a subsequence of length 4. So the whole thing must not be beautiful. So we can just return n and continue. Now, here we are building the vectors previous 0 and previous 1. If you have any doubt during any point, you can always pause the video and go through the code carefully. So here previous 0, we're setting it to -1, previous 1, -1. And then we'll fill this array. Okay, if we see a 0, we can update the value of previous 0 and previous 1. We just place it in this array. So at each position, I know where the previous 0 occurs and where the previous 1 occurs. Now, here initially my answer is 3. As we are looking only for length 4 subsequence, any subsequence of length 3 or less will always be not beautiful. So that's why that's the minimum answer, correct? So that's why answer is set to 3. Then we start at I equals 3 and go up to n, right? We start at I equals 3, go up to n. There's no point starting before that. And what we're going to do is basically, first we'll try to match the pattern 0, 1, 0, 0. So we go to previous 0, previous 1, previous 1, previous 0. And instead of, because I didn't want to write if else, if else, if else nested loop, that's why I wrote a counter to make sure that each of the steps happened, right? Even if one of the steps are skipped, we will think that it's a match, but it's not actually a match. It should match all four characters. That's why I have a counter over here. So once the counter equals 4, that means all these 4 steps have happened and we have matched all 4 steps, right? And in case these 4 steps have happened, I will check what is the valid length. Okay, I will check what is the valid length till how far we could have gone, right, without having a match. And across all the 4 matching strings, I'm taking the minimum of their valid length. Okay, so go basically says how far back we can go while still being not beautiful. If we go back any further, it will start becoming beautiful. So here we match for 0, 1, 1, 0, right? We also match for 1, 0, 0, 1. So previous 1, previous 0, previous 0, previous 1, and the same logic again. So to be honest, it's just ugly because we repeated the same thing. If we made a function, the code would look clean, I suppose. So yeah, here 1, 0, 0, 1, 0, 0, 1, 1. So first we need to match 1, 1, 0, 0. Now 1, 1, 0, 0. So we match that one as well. And finally, we take the answer, which is the maximum of the how much ever answer we found, as well as how back we can go here, right? And then we can print the answer. So that's how I approach this problem. If you have any better approach, you can drop it in the chat. My CodeChef ID is just my name, just Vibhaas, all in small. Vibhaas. I did the 2-pointer approach, increment left pointer until number of 0 is greater than 1, and brute force for substring of length 4. Okay, I suppose that would also work. So yeah, it doesn't really matter. As long as you understand the question is asking this, as long as you simplify the problem to this, after that, no matter how you solve it, really doesn't matter, right? Okay, let's just have some thoughts on problem D. I won't spend time reading the question, but I'm actually surprised there were so many solves, seeing how it's a segmentary question. I was kind of a bit confused, but yeah. Anyways, suppose you have two arrays A and B of length n, integer parameter k. We are defining a function score abk, and obviously, if you're just watching the PCD, I suppose you're going to read the question anyways, so I won't read it much. Basically, what it says is if AI plus k equals b, then we're swapping these two arrays and adding the elements. Then we add a to the score, and then we also have to handle these point updates. So it changes the value of some element in the middle to x, and then after each update, we need to output the value of the score. The updates are persistent. Even though the question doesn't say it, obviously the examples make it clear that the updates are persistent. Okay. And so I have not solved this or implemented this, so I can't really tell you. But towards the very end of the contest, when there were like 5 minutes remaining, I got like a rough idea for how we're supposed to approach it. And the idea was something like basically what we want is from a given node, what we're doing is at a given node, there are two things which matter. One is the sum, right? The current sum from what was there before. And then the second thing which matters is whether we are at A of I or B of I. Okay, so basically, instead of doing a swap, we can think of it as being a state of being in A of I or a state of being in B of I. Okay, so we can have a state variable which is 0 or 1, which means we are at A of I or B of I. By the way, if the explanation is not that clear, please don't mind it. This session was mostly to explain A, B, and C. D I did not solve, so I'm just giving a rough idea. Okay, so state means basically whether I'm at A of I or B of I. Okay, whether I'm at A of I or B of I. All right. And basically what I need to do in my segment tree is um, given my segment tree, I need to merge the children with their respective states. Okay. So if I have a particular, so my leaf elements, they are simply going to be for both cases. Okay. So for a leaf element, we simply have A of I, B of I, and state. Okay. If the state is 0, then it's just going to check if A of I plus K is less than B of I, and it will flip the state. It will flip the state if this is true and add A of I to sum. Okay. So each time the node is going to store two values, sum and state. Okay. Which is 0 or 1. So for the leaf elements, it doesn't matter. We can have leaves for both the states. But when we merge, I think it will start mattering. And then when we merge, what we need to do is basically we need to update the sum and state. And what will the state hold? The state is going to hold what state occurs when you start at some at 0, what you'll end up with if you go through these elements. Similarly, if you start at element at 1, state 1, what state you end up with. So basically what it means is if like each node in a segment tree represents an interval L to R, right? Each node in a segment tree represents an interval L to R. So if you enter at position L into the range L and R, okay? And your state is array A. So currently you're in array A, let's say. Currently in array A. Then after getting out of this interval, what will be your sum? After out of this interval, you need to know your sum. And you need to know which is the next state. Whether you are in array A, will you still be in array A or will you become in array B? Similarly, if you entered through array B, will you still stay in array B or will you change to array A, right? So that's what we need to know. So then when we have this kind of a segment tree, let's say we want a query of the whole range, we just need to query, let's say we want to query the whole range, right? So let's say we can break up the range into different parts and all we need to do is merge them together. So how do you merge them together? To go from a state, let's say 0 to 8, and this is 0 to 4, this is 5 to 8, right? So basically it's simply going to be the sum of both of them when we start at state 0. And what state will we come out? It will simply be pass this state to here, and what state finally comes out? So the final state will be the state of this 5-8 node after the state of the 0-4 node. So whatever the current state is, we're going to pass it to the 0-4 node. We'll get some new state. We'll pass that to the 5-8 node and we'll get a new state. So that's how we're going to perform merge operations on the segment tree. Okay. So basically the segment tree maintains two values. Which is the sum and the state. State means which array we are in. Sum means the sum of the range L and R if we start at a particular state. Okay. So I hope that makes sense. I'm not sure a simple implementation of segment tree can do it. I think you will need a more complicated implementation of segment tree, like a custom segment tree which has two values, sum and state, and a custom operation. Which is why, like, this is the only solution I can think of. Maybe there's a really simple solution that would explain the number of solves. Because if this is the solution, I do not see how there are so many solves. Or maybe just diff2 has become really good these days, I suppose. Not sure. Yeah. So that is a rough idea of it. If this has given you enough of an idea, you can try and implement it maybe today or tomorrow. Otherwise, you can always go through the official editorial, yes, whenever it comes out. All right, then we discussed problems A, B, C, and we had some hints for problem D. And we have come to the end of the session. If anyone has any general doubts, you can ask it now and I will answer it. Related to anything, your CP journey, your progress, Sublime text, whatever you want. Any of the problems which we discussed, you may ask it right now. Also, do check out TLE's course, guys. I know that many of you will be in the TLE course already, and many of you watch these videos regularly without being in the course, and you think you don't need it. And yeah, that's perfectly fine, right? If you're making consistent progress, then whatever way you're doing it is the best way. If you're not making consistent progress and you're stuck or you're not sure where to do You don't have peers who are doing CP. Maybe you're in a college where that culture is not there and you want something to help you out, then definitely do check out TL Eliminators course, right? I already mentioned that in the start of the video. It's in different levels and it has more than 40 hours of recorded lectures, 100 plus curated practice problems, hints, video solutions, doubt support by high-rated coders, as well as a leaderboard, right? Yeah. Okay, so looks like we got some doubts. I'm almost 1700 on CodeChef, but bottlenecked on 1400 in CF. Yes, don't worry about that because CodeChef is slightly higher inflated ratings than CF, okay? So CF is a harder platform because getting rating is harder on CF, I guess. So don't too worry too much, okay? I am also like, okay, my CodeChef and CF are kind of similar because I've not done much CodeChef. But usually for most people, their CodeChef is plus 200 or plus 300 of their CF. So you're roughly the same level, I think. If you're 1400, then you can take TLE's level 4 course, right? And the main topics, if you don't want to take the course, the main topics which you need to practice, binary search, combinatorics, dynamic programming, and graphs. So these will be your main topics. Additional topics should be DSU and segment trees. So 1400 means you're roughly specialist level, right? So that's what you need to practice. I am stuck on pupil for a long time. So again, if you're not in TLE, level 3 course would be for you, right? So as a pupil, you need to know you don't need to care that much about DP right now, but what you need to care about is binary search, number theory, combinatorics, greedy, right? Binary search, number theory, combinatorics, greedy, and two pointers as well. A lot of times, two pointers can be done with binary search as well. So yeah, these are the rough ideas you need. If you already have theory and you're struggling to gain rating, if your theory is good, your problems are good, and you're struggling to gain rating, in that case, I recommend doing virtual contests. Go to CF, go to virtual contests, do them religiously, do a virtual contest every 1 or 2 days, and within a few weeks, you will see definitely your performance improving. Okay? Do the past 20, 30, 40 contests as virtuals, and obviously absolve after the virtual contest, you will definitely see very like straightforward improvement. Okay, looks like not much doubts tonight. So then we'll end the session. Thank you for attending, everyone. Hope you learned something and have a good night. Right? How many questions should you upsolve? So usually when you solve in a contest, let's say you solve 3 questions, then you should definitely upsolve the fourth question. And sometimes if you feel easy, you should upsolve the fifth question. So most contests are made such that you definitely you upsolve 1 question, and sometimes you can upsolve 2 questions more than what you solved during the contest. Okay. That's the golden rule for upsolving. Okay, then. Good night, guys. Gonna end the session now. Thank you for attending and see you next time, hopefully with more solves. Yeah. Okay. Bye bye, everyone.